In the previous lecture, I explained the method of finding out a lower bound for the variance of an unbiased estimator for a given parametric function. As I mentioned, it was derived independently by three statisticians, Frechet, Rao and Kramer, and therefore, we have named it as a Frechet Rao Kramer lower bound, that is FRC lower bound for the variance of an unbiased estimator. We have seen that there are cases where we can find out an estimator for which this lower bound is attained. There are also cases where it is not attained. We gave a condition under which an unbiased estimator will attain this lower bound. The condition was in the terms that it should be linearly related with a function Sx theta with probability 1. This method, as I explained, this method of lower bounds is very useful from 2 points of view. One is that given any estimator, we can compare its variance with the lower bound, and therefore, we know that how far we are from the actual, and that means what could be the best possible way minimum variance and where are we, that means where is our estimator standing in its relative position. And second thing is that if we are able to obtain an estimator for which it is equal to the lower bound, then certainly it is the minimum variance unbiased estimator, that is among the unbiased estimator it will be certainly the best. So, from this point of view, this method of lower bounds is extremely useful. We have seen that FRC lower bound, as I call it, is dependent upon certain regularity conditions, that is when the density or the mass function under consideration satisfies certain conditions, then only this lower bound is valid. We also see in this what are the parametric functions for which this lower bound is attained. So, let me give it in the form of a theorem. So, we have a random sample x1, x2, xn, and we know that the FRC lower bound for the variance of an unbiased estimator of say g theta is attained, then what are the parametric functions apart from g theta for which this will be attained? Then the answer is that they are actually the linear functions of g theta. Then the class of parametric functions for whom the unbiased estimators attain this FRC lower bound, then this class is the class of linear functions of g theta. Like I said, what is the unbiased estimator for which the lower bound will be attained? That should be a linear function of Sx theta with probability 1. Now, what are the parametric functions for which it will be attained? Then they should be simply the linear functions of g theta, that is the statement of this theorem. Let me prove this theorem here. So, let us consider say Tx, let Tx be an unbiased estimator of g theta, and let variance of Tx equal the FRC lower bound. Then certainly we know that Tx and Sx theta they are linearly related with probability 1. We will use this with probability 1 as an abbreviation here. So, that means there exist functions say alpha theta and beta theta such that say T x plus alpha theta S x theta is equal to say beta theta with probability 1. This should be true for all theta. Okay. Now, in this relation, let us take expectation on both the sides. So, expectation of T x plus alpha theta expectation of S x theta is equal to beta theta for all theta. Since this statement is true for all, that means for random variable x, here it is true with probability 1. Therefore, it is possible to take the expectations. Basically, expectation means either we have taken summations or we have taken the integrals or a mixture of the two. Therefore, we will get expectation of this equal to beta theta. Now, T is unbiased estimator for g theta, that means g theta. Now, expectation of S x theta, that is 0. Therefore, this is simply giving you beta theta, because this is equal to 0. So, in this relationship beta theta has turned out to be g theta here. Now, let us consider let h theta be any other parametric function for which there exists an unbiased estimator for which the lower bound is attained. Okay. So, for which there is an unbiased estimator say u x such that variance of u x attains the corresponding FRC lower bound. We have seen that even if we change the parametric function, the lower bound is changed, but the condition for attaining the lower bound remains the same. Therefore, so there will exist that u x and S x theta are again linearly related with probability 1. That means, we can say that there exist say functions alpha star theta and beta star theta such that u x plus alpha star theta into S x theta is equal to beta star theta with probability 1 for all theta. Once again, since this statement is true with probability 1, we can take expectations. So, if we take expectations, we get expectation of u x will be equal to h theta plus alpha star theta into expectation of S x theta is 0 is equal to beta star theta. So, we are getting h theta is equal to beta star theta. So, if we look at these two equations now, T x plus alpha theta S x theta, that will be equal to g theta, and ux plus alpha star theta sx theta is equal to h theta. So, we have Tx plus alpha theta Sx theta is equal to g theta with probability 1 for all theta, and ux plus alpha star theta Sx theta is equal to h theta with probability 1 for all theta belonging to theta. If this relationship is true for all theta, we can fix a value of theta. Fix a value of theta, say theta star, or let me put theta naught, because already so many stars are there. So, in that case we can write the relationship as Tx plus alpha theta naught Sx theta naught is equal to g theta naught with probability 1, and ux plus alpha star theta naught Sx theta naught is equal to h theta naught with probability 1. That means, what I have done is that these two relations I have written for a fixed value of theta, that is theta naught. Now, in both of these equations Sx theta naught is appearing, so I can eliminate that. So, eliminate Sx theta naught from the two equations. That is, in the first equation multiply by alpha star theta naught, in the second equation multiply by alpha theta naught and then subtract. So, we get alpha star theta naught Tx minus alpha theta naught Ux is equal to alpha star theta naught g theta naught minus alpha theta naught h theta naught with probability 1. Now, once again you can take the expectation, because what is happening here is that this coefficient is a fixed number, this coefficient is a fixed number, and right hand side is also a fixed number. So, we can say that a times say Tx plus say b times ux is equal to c, where a, b, c are constants, and this statement is true with probability 1. So, we can again take expectations. If we take expectations, we get a times g theta, that is expectation of Tx, plus b times h theta is equal to c. Now, you look at the significance of this. I started with a function g for which the FRC lower bound was attained. I assumed h theta to be any other parametric function for which the lower bound is attained, and now we are getting that such g and h will be related using linear relationship here. So, g and h are linearly related. Therefore, all functions for which the FRC lower bound will be attained, they will be linear functions of g. Now, in yesterday's lecture, I have given examples. In some examples, the lower bound was attained. Let us take one such example. Say Poisson distribution. So, we had x1, x2, xn following Poisson lambda, where lambda is positive. We have seen that x bar was unbiased for lambda and variance of x bar was lambda by n, which was also the FCR lower bound for unbiased estimator of lambda. So, if I consider say lambda square, let g lambda be equal to lambda square. In that case, what you will get? The FRC lower bound for variance of an unbiased estimator of G lambda. Now, that will be equal to G prime lambda square into the FRC LB for lambda. So, this will become 2 lambda square, that is 4 lambda square, and this is lambda by n. So, it is equal to 4 lambda cube by n. Now, let us consider, say, y is equal to sigma xi. Of course, this will follow Poisson n lambda, and you can look at y into y minus 1 by n square. Let me call it to be, say, u. Then expectation of u, it is equal to 1 by n square expectation of y square minus expectation of y, that is equal to, now this will become equal to n lambda plus n square lambda square minus n lambda, expectation of y square is n lambda plus n square lambda square, because if we consider Poisson distribution with parameter lambda, the second moment is lambda square plus lambda, and expectation y is equal to n lambda. So, this divided by n square, so that is equal to lambda square. But if we consider, say, variance of u, that will be equal to, this can be calculated easily, that will turn out to be, because this will involve expectation of u square minus expectation of u whole square. Now, expectation of u is lambda square, and expectation of u whole square will involve expectation of y to the power 4, expectation of y cube, and expectation of y square, which is available. All the expressions are there for the Poisson distribution. After simplification, you get it as 4 lambda cube by n plus twice lambda square by n square. Now, you can easily see that this is bigger than 4 lambda cube by n. It is understood that this statement should be true, because lambda square is not a linear function of lambda here. We have already shown that for lambda, the variance of the unbiased estimator attains the lower bound. Therefore, all other functions for which it will be attained, they will be of the form a lambda plus b, and this is lambda square. So, certainly this cannot be attained. Later on, we will show that actually this is minimum variance unbiased estimator using another method. Let us consider general form of an distribution in the exponential family. So, let us consider a density in the exponential family. What is exponential family? The density is of the form c theta hx e to the power q theta tx. Now, if we have a distribution of this form, it is said to be a distribution in the exponential family. We can see examples here. Say x follows binomial np, where n is known. Then the form of the distribution is ncx p to the power x 1 minus p to the power n minus x. This we can write as ncx 1 minus p to the power n p by 1 minus p to the power x. This we write as 1 minus p to the power n ncx e to the power x log p by 1 minus p. So, if you compare it with this form here, you have a function of the parameter, that is c theta, here theta is p, hx is ncx here, e to the power q theta tx. So, here q theta is a function here log p by 1 minus p, and x is the term tx. So, this is a distribution. So, binomial distribution with n known is in exponential family. Let us take some more popular examples in the statistics. Let us consider, say, x following Poisson lambda distribution. The form of the probability mass function is f x lambda. It is equal to e to the power minus lambda, lambda to the power x by x factorial. This we express as e to the power minus lambda 1 by x factorial e to the power x log lambda. Once again, if we compare it with this particular form, you can see here e to the power minus lambda is a function of lambda, 1 by x factorial is a function of x. So, you can call it hx, x can be written as tx, and q theta, it is log lambda here. So, you can easily see that this is also a distribution in exponential family. We can actually also consider this, we can consider as a one parameter exponential family. We may also consider multi-parameter exponential family. Here parameter could be multi-parameter here. So, here we write c theta hx e to the power sigma qi theta t I x, I is equal to 1 to k. So, theta could be, say, p dimensional, and we may have this particular form here. So, this is actually called, see, if we have the same dimension here k, then this is called a k parameter exponential family. Let us consider, say, x following normal mu sigma square. Here both mu and sigma square are unknown. F x mu sigma square we can write as 1 by sigma root 2 pi e to the power minus 1 by 2 sigma square x minus mu whole square. This we express in the following fashion. If we expand this term, you get a term mu square. So, you get minus mu square by 2 sigma square, and there is 1 by sigma here, 1 by root 2 pi. You have e to the power minus x square by 2 sigma square plus mu x by sigma square. Now, this is a function of parameters here. So, this can be considered as a c theta function. This constant 1 by root 2 pi can be considered as a function of x alone, and then you have, you can write here T1 x is equal to x square and q1 theta is equal to minus 1 by 2 sigma square. Similarly, here T2 x can be taken to be x and q2 theta can be considered to be mu by sigma square. So, this is a distribution in 2 parameter exponential family. most of the standard distributions in statistics that we use, for example, gamma distribution with r known and lambda unknown, that is a distribution in exponential family. If we consider a negative exponential distribution with the scale parameter, that is also in the exponential family. So, there are various distributions which are actually in the exponential family. Now, exponential families have some important feature, and in particular with respect to the FRC lower bound. So, let us consider in the context of the lower bound. So, if we are writing one parameter exponential family as let us take log of this, that is equal to log of c theta plus log of hx plus q theta tx. If we consider the derivative of this with respect to theta, we get c prime theta by c theta plus tx into q prime theta. Now, if you remember your Sx function, it is nothing but sigma del log f xi theta by del theta for I is equal to 1 to n. So, this becomes simply n times c prime theta by c theta plus q prime theta sigma t xi. Now, you see here, this is constant as far as variable is concerned. So, this is actually a linear function of sigma t xi. So, Sx theta is a linear function of sigma t xi. So, in the distributions which are in the exponential family, the variables, or you can say the estimators which are linear functions of sigma t xi, the variances of them will be attaining the lower bound for the estimation of the expectation of this. So, what we are saying is, let us call it say W, that is 1 by n sigma t xi. So, this is linearly related with Sx theta with probability 1. Hence, any linear function of W will be attaining the FRC lower bound for the variance of expectation, for the variance of unbiased estimator of expectation W. We can also see that what will be this expectation in general. See, in this particular case, see, we discussed some examples like a Poisson distribution. Now, in this Poisson distribution, if you see, c theta is e to the power minus lambda, its derivative will also be equal to e to the power minus lambda. So, you will get minus n here, and q is log lambda. So, q prime will become 1 by lambda. So, you are getting minus n plus lambda, and this will become sigma xi. So, when we say v, v is equal to x bar, and this w is equal to x bar here. So, x bar is attaining the FRC lower bound for expectation of x bar, that is lambda. So, we have already proved this statement. I am just once again demonstrating that if the distribution is in the exponential family, then all the linear functions of 1 by n sigma t xi, they will have variance equal to the FRC lower bound. So, this is a remarkable thing. Whenever we are having distributions in the exponential family, there will be certain parameters for which the lower bound will certainly be attained. Now, let me also obtain the expression for this what is expectation of W. So, let us also determine expectation of W here. So, that will be, let us consider the integral or the summation of the density function or the mass function will be equal to 1. So, I have written a general Lebesgue-Stieltjes integral, meaning that it covers the discrete and continuous cases both. So, c theta h x e to the power q theta t x is equal to 1. Now, we make certain assumptions here, like differentiation under the integral sign will be assumed, because in the Rao-Kramer lower bound itself we make certain assumptions, certain regularity assumptions. So, that assumption should be true here also. So, if we assume that, then we can differentiate under the integral sign. So, we will get, here there are two terms which involve theta. So, if we take the first one, we will get c prime theta h x e to the power q theta t x d mu x, and if you differentiate the second term, you will get c theta h x e to the power q theta t x into t x d mu x, and of course, q prime theta will also come. This is equal to 0, the right hand side is 1. So, the derivative is going to be 0. Now, this term we can write as divided by c theta multiplied by c theta, then that will be integral of the density once again. So, that will become equal to 0. If you look at the second term, this density is as such, then you are getting this term as additional term. So, q prime theta expectation of T x, this is equal to 0. That means, what we are saying, that expectation of theta, expectation of T x is actually equal to minus c prime theta by c theta into q prime theta. Consider, for example, the case of Poisson distribution. In the case of Poisson distribution, c was e to the power minus lambda. So, c prime theta by c theta will become equal to minus 1, that is minus minus becomes plus, q prime theta, that will become 1 by lambda. So, if you put it in the denominator, you will get lambda here. So, in the case of Poisson distribution, this will become lambda. Sigma of T x I by n was x bar. So, the statement is that x bar will attain f r c lower bound for the estimation of lambda. So, that statement we verified directly. Now, if we are having the distribution in the exponential family, this will be always true. Let me take one more application here. Consider, say, geometric distribution. Yesterday we have seen here the form of the distribution, we have taken theta into 1 minus theta to the power x for x is equal to 0, 1, 2 and so on. So, we can write this is equal to theta e to the power x log 1 minus theta. So, here c theta is equal to theta. If we compare with the distribution in the exponential family, h x is 1, t x is equal to x and q theta is equal to log of 1 minus theta. So, naturally minus c prime theta by c theta q prime theta, that is going to be equal to minus 1, c theta is theta, q prime theta will become equal to minus 1 by 1 minus theta. So, it is equal to 1 by theta minus 1. That means, and here x T x is equal to x. So, W is equal to x bar. So, expectation of W, that is equal to expectation of x bar, is equal to 1 by theta minus 1, and variance of x bar will be attaining the Rao-Kramer lower bound, will be same as the FRC lower bound for estimation of 1 by theta minus 1. Now, if we consider a linear function of it, so 1 by theta also we can consider. So, we can say that x bar minus 1 is minimum variance unbiased estimator for 1 by theta. So, this statement is also true.